Hello and welcome to the SaturdayMP Show, episode number 40, being recorded mostly live, April 8th, 2024. This is a show where we mostly talk about shipping secure, high-quality software faster. And today we're going to do that by kind of doing a deeper dive into Unicode and some binary bit math. Because a while ago, I tried some of these picoCTF, pico capture the flag problems, and this one here, called transformation. I got a solution for it, but it was with the help of GitHub Copilot, and I haven't done binary math, and Unicode still confuses me a bit. So I figured I'd come back here and figure out why this solution worked, and just kind of explore some of the math behind how this encoding worked. So you could see that in the previous video in SaturdayMP Show episode number 36. This is where I actually solved the problem, but kind of like I said, GitHub Copilot eventually shows up to save the day. I was struggling with some of the binary math to get it done there, so you can go watch that if you'd like. Yeah, that's basically what we're gonna do today. So and today is also April 8th, so it's an eclipse day. So if you're on the path of the eclipse, I hope you're able to see it up here in Edmonton, Alberta, in Canada, where I am. I think there's maybe like a third of the sun will be covered, but it looks like a nice sunny day. And it's not supposed to happen until about noon, so I think I'll head out there later today and see if I can see any of it. Hopefully not go blind looking directly at it. So, all right, so let's just jump right into this. So the original transformation problem basically gave you this Python encoding one-liner, which I've caught, which is up here now. And it also gave you this file that was encrypted, the encrypted file, which is actually these, I think they're mostly Chinese, but some sort of Asian, I know a little, looks like Cantonese kind of characters. And then your job was to decode them back into English. And then that was basically the flag that you got. So, but in our case, I'm gonna just go through both of them here. So this is the simpler one. Like I just want to encode A, B, C, D, and we'll encode it, and we'll print off the encoding. And then obviously I've solved the problem. So I guess spoilers, if you want to solve this problem, there's the answer right there to decode it. And then, but what I'm really curious about is some of this binary math and how Unicode works in a little more detail. So I spent kind of this weekend exploring, digging around Unicode. So Python, I guess the first thing I had to check out was how did Unicode, because there's lots of different ways to do Unicode. So how did Python do it? And by default, Python uses, I'm trying to remember, like I watched a video and did some more reading. Python uses the most efficient algorithm possible. So if you just have Latin characters like kind of English and French and stuff, it'll just use UTF-8, but it'll encode things like that. But if you start using other characters, then it will actually bump it up to 16 or 32. Like it basically uses the best encoding it can for the characters in your string. And all strings in Python, so this string here, flag, this encoding, this decoding, these are all Unicode strings. So by default, Python 3 at least uses Unicode for everything. And I think that slowly got rolled out in Python. I think Python 3 switched everything to Unicode, and then it slowly got rolled out, is my understanding. So I have this handy dandy Unicode lookup table here, so we can actually see the characters. We got this, oh yes, you can see me mucking around with some stuff. You can, the hexadecimal, so we can convert hexadecimal to binary. It's just me looking up integers. All right, we don't need SaturdayMP Show. I guess if you like these videos, click like or subscribe, but we don't need this anymore. Yeah, so let's see how well I can explain this to myself and to others. So what this encoding actually does, I guess let's just run it real quick. So if we go, again, my default is Python 3, example.py. Right, so it's going to take the flag, which is ABCD. It's going to encode it using this secret encoding thing. So again, in the challenge, you were just given this, the encoded string and the encoder, and then you had to write the decoder. So we print off the encoded thing, which prints out these Asian characters here, and then we decode it and we get back to A, B, C, D. So what it's doing is it's taking this 4 characters here and combining them into 2 characters. Excuse me. And then the decoder actually has to decode it. So like if you try A, B, C, D, E, like this I think this fails. Yeah, you get an error because this has a length of, like it always assumes there's the 1 character and then you have to combine it with the 2nd character. So, all right, so the way, let me move this up a little bit here. There we go. So the way, as best I could tell, so the way this works is if your encoding is A, B, C, D, so flag at I, so for those that don't know Python very well, like I struggled with Python for a bit too, this is basically a for loop, and it's just going to loop over the flag, which is A, B, C, D, every character in the flag, and it's going to jump by 2. So I will jump by 2, so it'll start at 0 and then go to 0, then 2, 1, 2, yeah, 0, 1, 2, yeah, 0 to 2, and then, well, then it's the length of the flag is 4. So when it hits 4, it's done. So we can kind of ignore this part at the end here. That's just the for loop part. What we're really interested is this middle part here, which basically says this, you just need this to start an empty string. So take a string and then add to these strings all the characters inside this bracket that you find. And what it's doing here is it's taking the first value of the flag, so in this case A, it's figuring out the ord. So ordinal, we'll go over that in a minute, but that just basically, that gives you so one way to think of Unicode is a giant mapping of numbers to characters. So if you actually go, I have that one Unicode lookup one there, but if you go to Unicode here, oh, not Wikipedia, sorry. If you go to this one, and then there is the code charts here. So say you want to look up something in here. So these are all the charts. Basically, they tell you what that maps a number. So if we do Latin, basic Latin, this is like ASCII. This is the original one. It's going to say that 0 maps to null. And then if we want to find, yeah, 0, 0. If you want to find like A is this character here. So basically this hex value or this decimal value, if you want to think of it, is going to get mapped to capital A. And every one of these is going to have a different, and so they've broken them all up. So if we look at, I don't really know any Arabic. So, but again, you're going to see the same thing. It's just going to map, it's just a way of mapping a number to a unique character or a glyph or however you want to refer to it for all these different language, right? So, yeah, I don't know anything about Arabic, but I've always liked, it's kind of a cool language. In our case, I think these are Cantonese characters, so, or Chinese at least. So let's, African, South, is it South Asian? I think it's this one of these ones here. Oh yeah, there's a ton of characters too. So let's see, this will be a big one. Yeah, so basically we're just mapping to these different characters. Oh yeah, and there's a whole bunch of different, slightly different ones. For a little studying of Cantonese and Chinese language I've done. It's a very tough language, at least for me to learn. So yeah, you can see there's different, like this one maps to this. So that's all it really is. And so this is called, from my understanding, it's called a code table. So that's what this ordinal will get you. So if you look up, whoops, Python, maybe it's already in here. Let's see, does it have the ord? Oops. Right, so here, yeah, so code points, I guess. Sorry, that's what it's called. So like 0061 is kind of a way to map to smaller case a, where, you know, these ones map to Roman numerals, these ones map to emojis. And we can see that here if we go look in this Unicode lookup table. So unfortunately, the Unicode site itself, I couldn't find anything to look it up. You had to go look at all those actual specs. But if you go here and look this up, right, this is yeah, digit 1. I thought that should be small a. 0061. Uh-oh, now I'm confused. All right, if we copy this one, do I get the right? Oh, wait, this is hex, I think. Yeah, there we go. Okay, sorry, these are hex values into the Unicode chart. So 0061, go here, there, small a. So it's just a way to look it up. So there's different ways to look it up. You can look it up by the decimal number, hexadecimal, binary number, all that stuff. So if we looked up decimal, I think decimal 97 would get me. Yeah, small a. So all right, so that's basically how that magic works. So when we go here, we got flag of I, so the a. So let's just bring up Python. And if we just do ord of, in our case, it's smaller case a, it's going to give us 97, which is, if we did the hex of that, it should be 61, I think. So if we did the hex of ord of a, yeah, 61. So, so that's what this gives us. We basically convert this glyph, or this character, we're going to convert it into a number, and that number represents the index. Like, one way I like to think of Unicode is a giant array of like millions of characters, and this gets you the index into that array of what characters should be shown. So that's what this first part does. And then the second part, this is actually a bitwise operator in Python, and it says shift the bits, shift all your bits to the left 8. And so for those that don't know, so there's a bit, and then, oh, no, I guess I should put it like this. So there's a bit, and there's a byte, which is 8 bits, and then there's word, I guess. There's different ways to describe this. Sometimes you'll see it's different, but then there's a word, which is 16 bits, and then double word, or I think long. It depends on your operating system. Long is 64 bits, but so this is kind of a way to describe things. And then when you have a hex, a nibble. So there's actually, hex is actually 4 bits. It's just a nice way to write 4 bits. So if you have the hex value of 0x61, this actually gets translated into, I have to remember. Here we go. 61. That's what it gets translated into. So you can see the math below. Here's a hex to binary converter. But you can think of it as 4 half a byte. So a nibble, I guess, which is 4 bits. So the 1, this 1 here, corresponds to 0001, right? And then this 6 here corresponds to this 0110. And for those that remember your binary math, this left, or this right, in our case, the rightmost digit is the smallest one. So this is 0, this is 1, this is 2, this is 3. So this is the 0 to 1 bit, this is the 2, 4, and then 8 when you're figuring out the number, and this one's 0, 1, 1, 0. And hexadecimal will go from 0 to F. So that's what hexadecimal goes from. And oh, look at GitHub Copilot, so creepy. And so that's the representation. So it goes from 000 to 11111. So that's just so those who don't know. And then I had to remind myself about how all this worked the other day. So that's what we're going to do. So we get this hex value of this. So in our case, this hex value of, so let's just move all that down. If we have 0x, so you can, the 0x just tells you that's hex. You can ignore that part of it. Most languages do 0x, but this is just kind of a Python thing. I think a lot of other languages do that. So this actually, if you remember, it was 0110 001. So we can leave that all as 1. So now if we're going to shift all those bits to the left, this is where I had to look up how Python integers work too. So Python integers are actually, at least in Python 3, they are actually a class. It's not like C or something like that, where you have an integer is maybe 16 bits or 32-bit integers. I wanted to see what the maximum type was. But apparently, so I don't know how, under the scenes how it works, but from what I could tell from playing around, it's just a class. It has unlimited size of integers. Like if you want to see what's the max integer size, in C, you're going to get limits to that depending if it's a 16, 32-bit, or 64-bit integer. In Python, they just say it's unlimited because this integer class, this Python integer class, does all the magic underneath it. Right, so here's integer. So best I could tell, what happens is when you shift the bits to the left 8, it's going to actually do 0, 1, 1, 0, 0, 0, 0, 1, and then 1, 2, 3, 4, 5, 6, 7, 8. So that's what this flag does here. Is it basically, if you wanted to, you could think of this first number like this. There's a bunch of leading zeros in front of it. And then what it does, that shifting to the 8, is it moves everything to the left. So what this gives us a much bigger number now than before. So if we want to figure out what the number is, how the heck do I do that again? What is that? So it's going to be 6100. That's our number. 6100. I think is that right? 61. Yeah, it should shift it like that. So that's going to give us this number here, and as a decimal. So let's go see. So I think. Okay, now again, this is mostly live. So this is me learning with you. So if you want, I guess I didn't say this at the beginning, but if you want more polished videos, try a different one. We're gonna probably struggle a little bit here. Okay, so I'm gonna run my script again here. Oh, I'm not in the right folder. There we go. Okay, so this is the character we want. So let's see. Oh, that's oh, sorry, let me try. Oh, sorry, this isn't quite the character we're going to get, because first of all, it shifts those bits over by 8. So we end up, this first part ends up with this number here, which I guess we could look this up in Unicode. Maybe let's see if this is a valid Unicode value here. What was I was going to look up 0x6100. Okay, well, is it a CJK? Is that Chinese? Something. My apologies for not knowing this. If you do know this or understand this a bit more, let me know. I should actually have ran. Actually, I probably should run the string through Google Translate or ABCD. Hopefully, we're not saying anything too offensive. So you're going to end up with this character. But the other thing we're going to do is we're going to add the next character. So in this case, we're going to add B. So let's mark this as A. So this was the character A. Now the character B is going to be 0x. It's actually 62 because it's the next one. So for those who don't know, ASCII was like one of the first kind of character sets that ever came out, and you could represent that with like 7 bits. 7 bits, I think. So let's see, ASCII table. So, and way back in the day too, I used to have this ASCII table. Can I make this bigger? Yeah, okay. Oh, this isn't the, it's kind of a gross way to represent it. Okay. Is there a better table? I had found a better table before. Yeah, I think this one. Yeah. So here's the ASCII table, right? So it goes up to 127. And then if you want to find, like here's lowercase a is right here. Whoops. Is 97, hexadecimal 61, and hexadecimal 62 is B. So when Unicode first came to be, or when Unicode was created, because ASCII kind of existed as the first, I don't know what you would call it, like language, like mapping of bits to characters. They just basically mapped this one-to-one to Unicode. There was no change in it. And for those that maybe remember back in the day, or did programming in Windows or something like that. I don't know if Linux had this problem, but when I did Windows programming, you had different, what the heck were they called? Like character tables. So if you wanted to do a different language, you could load like the Latin 1 character table, which had some of these extended. So Latin 1 was basically all the ASCII plus, if I remember correctly, all these extended characters, which gave you some French and Spanish. And probably other ones that I don't really know, and some math symbols. But then if you wanted to load like a language that you couldn't represent by ASCII, say like, I don't know if Russian's in here, like some of the more, or definitely Arabic. I don't remember how they handled Chinese back in the day because they didn't have an alphabet. But you would load a different code table, and it would just Windows, and that way it would know like, oh, if you entered the character 50 in decimal, instead of getting a 2 back, you would get whatever the equivalent in that language was. So it used to be all these different code tables, but that was really confusing, hard to work with, and it was really hard to mix languages. So that's where Unicode came about as just kind of one mapping to rule them all. So instead of being limited by 1 byte, they just said, no, I think Unicode can go up to 4 bytes. UTF-32, I think, is encoding. And I don't think it's full yet with characters, but yeah, it had enough to cover all the languages, apparently, plus they still had room for all the emoticons and stuff like that, and other weird picture characters. So anyway, there's a little bit of history, but yeah, that's how ASCII worked. So that's why I know it's 062. Which translates into, is Google Copilot right? Let's see. So this part's going to be the same. Yeah, and then we just went from 1, 0, 0, this is 2. Yeah, all right. And then if this one we don't shift though. We're just adding this number. So we're adding these bits to these bits. So when we do that complete math, let's just do total. Right, we're going to get 0, 0, 1, 1, 0, 0, 0, 0, 1. And then the next one's going to be 0, 1, 1, 0, 0, 0, 1, 0. So when you're adding, right, like none of these, like, it's just like base 10 math. You're going to add 0 to all this. It's just going to be what this one is. And then when you add all this to 0, it's just going to be what this is. So now we get this number, which we can represent in hex as, 6162. Or if we want to stick with our, just so we can see, maybe we'll put it here, 0x62. All right, and that as a decimal number, I have no idea what that decimal number is. But if we go look up this Unicode number. So it's 6162, like this. We should get this same, I think, it's kind of small. It looks like the same character to me, 6162. Can I make this bigger? Let's see, view. I really miss being on the Mac sometimes, where it's like you just scroll in and it'll automatically zoom for you. Oh, there we are. Control plus, zoom in. All right. Hopefully that's a little easier to see. So you can see this character here. Let's just put these up here too. So hopefully, like, yeah, I'm sure if you're a native reader of this language, you can read it no problem, but that looks like the same character. So that's how that one was encoded, and it'll be something very similar for the second encoding. For the second, for CD, will give us this particular character. Now, the thing that I struggled with was the decoding, but I think I've kind of already answered my question. So to decode this, you basically have to undo this binary math that we did. And the way GitHub Copilot suggested to do it was to first, so this is I think this is a part that confused me, the 0x111. So in this case we have, so this is our decoding that we're decoding. So let's move this up here so we can see the decoding thing too. Okay, so this is what we're trying to decode. We have these 2 bytes, and this first part. So let's do this in math order here. So this first part, so instead of the flag, we're just taking the encoding of 1i, which is this particular character here. I guess let's put this up here. Oops, there's the 1 character. Okay, so we need to decode that, and it should be A and B when we're done. So the first thing we do is we take that and we shift the encoding to the right 8. So that is going to give us 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this just shifts this over here. And the char command in, I don't think I discussed the char command. The char command in Python converts that integer, or that index, into the Unicode, giant Unicode array that ORD gave us, back into a character. So if we go to here and we did like, so yeah, so we got the ORD of A is 97. If we do the char of 97, that'll, char, oh, whoops, not char, just CHR. There we go. All right, there's A. Okay, so we shifted all those bits over, and now because this is 0, like, we can effectively ignore anything, just like numbers in base 10 math. If you have 0, 85, right? If that was your number, you can, that's the same, like 0, 85 is the same as just 85 in base 10, right? You can ignore those zeros to the left of it. So this gets us A, right? So this, if we put this in hex, this is 0x00 and 0x61. Okay, so this gives us back to A. So if we were to enter this into our Unicode lookup, 0061. Yeah, small Latin A. Okay, perfect. Now if we go, so this one, and what does the ampersand do in Python? I think that, is that a bitwise OR? All right, let's take a look at ampersand in Python. Oh, it's a bitwise AND operator. Okay. So that means it just, so the way AND works, for those that don't know, if you have, just for AND, if you have something like 1, and I guess the chart's right here. But if you have 2 bits, I guess we're talking at the bit level. If you have 1 and 1, that equals 1. If you have 1 and 0, that equals 0. If you have 1 and 0, 0 and 1 equals 0. And the last one is 0 and 0 equals 0. So you're going to end up with a chart like this. So basically, the only time when you bitwise AND 2 numbers or 2 bytes together, only if both of the bytes are 1 do you put 1 in there. So if we go and look at, okay, so we have the second part, the encoding at I. So it's the same I, so we have the same character. So we start with this again. So let's lump that together a bit. So let's create another one. So we start with this, and then we're going to multiply, or we're going to do the bitwise AND to 0xFF. So 0xFF is 0xFF equals basically that. Everything is 1. Okay, so we're going to, our math is going to look like, maybe we'll put another line here. It's going to look like 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0. And then the line underneath is going to be a bunch of zeros, and then 1, 1, 1, 1, 1, 1, 1. Okay, so this is basically, this could be the same as writing this. Okay, this kind of answers my question now, because we're basically going to cancel out this top part to get the bottom number again, which is B. So when you do the math, so we did the bitwise OR, so 0, 0, these are all zeros. This is 0, 1, 1, 0, 0, 0, whoop, 1, 0. Right, because these two are 1, this is a 1, this is a 1, so it's a 1 down below. I guess we could equals. How do we want to do this? I don't remember how to write actual bitwise. And then we can just put equals. Maybe we'll just do that. There we go. All right, and then that gets us our B character. So this char here becomes A because this is the character it is. So the looks up 61, and then this is the character for there, and then yeah, I guess this is technically this is B. B. Okay, cool. Okay, so that's how that decoding worked. That GitHub Copilot just dropped in my lap, and again we can ignore this. Is just loops over all the characters in there, breaks one character out into 2. Okay, cool. Well, so I did some of this research today, and this helped just kind of solidify it going through this example. At least for me, I found that pretty useful. So it's been a long time since I had to do, back in university days, we had to do binary math, like on paper. That was our exam. The first year, I remember, first and second year, they would give us like, add these 2 numbers together, or take these numbers, translate them like into base 10 into binary, and then add them together. And yeah, and then they would also do things like, oh, let's do like base 4 math or something like that, just to, so the only you could only represent like your digit. So base 10 means you basically can go, one space can be represented by 10 different digits from 0 to 9, right? So it's 10 digits. For base 4, you can only represent 4 digits, like binary is 2s, you got 0 and 1. Base 4 is like you got 0 to 3. So it's just different ways of doing math with a different base representation, where base is how many digits, how many different, I don't know how to word that. How many digits do you have for one space that you can represent for one column, I guess. Yeah, okay, cool. Yeah, I haven't done a bunch of that in a while. This was a lot of fun. Because I think when I did the decoding, this part made sense, right? Like I shifted it to the 8 and then I wanted to unshift it. But then I was confused about this, and this was basically saying just cancel out everything to the left. Cancel out that left byte, and then you get back the original one that you had there. So, because otherwise you're left with the bigger one. Yeah, okay. Anyway, that's how the decoder works. So this is basically answering my own question. If you have a question you want me to answer in the future, please send an email to ask@SaturdayMP.com, or assuming you're watching this on YouTube, leave some comments down below with questions and stuff like that. You can also send me, constructive feedback to ask@SaturdayMP. If you liked the video, if you liked what I did here, and you think others would find it useful, please share this video with others, and then clicking like and subscribe makes me feel good, but the main reason is to also make others find it, so when they're searching for things like binary math or Unicode or something like that, maybe they'll come across this video and this will be useful for them. Or if they're searching for like how to the picoCTF was it picoCTF transformation problem, which apparently a lot of people liked. They didn't like this problem. Yeah, maybe it'll help them understand it better. So thank you very much everyone for watching. I hope you have a good day, and I hope, hopefully if you're watching this in by the time this comes out, the clips will be gone because this won't come out till like Wednesday or something, but I hope if you're in the path of the eclipse you were able to see it and it looked really cool. So it's looking like a really nice sunny day in Edmonton, so I'll probably get somewhat cloudy, I'm assuming, just a little eerie, but it won't get super dark like it will in some places. So anyway, take care and enjoy the rest of your day. Goodbye.